Okay, guys, I want to take a few minutes here to do the quick post lab from the Newton second law lab that you did on the computer the other day. I'm making this in case I'm not in school. I'm getting my COVID booster shot, and I anticipate being in school, but if I'm not, I'm not. In the front of the room, in the black um, file system on the front, you can pick up your labs from the other day, and you should get your lab. And if you want to sit next to your lab partner, you can. Otherwise, I'm going to sort of walk you through what you should have seen from the lab. The data obviously worked out perfectly. The graphs are great. You did a great job in the lab, so that was excellent. I just want to make sure you understand the whole point of that. You're basically deriving the equation. I want to show you how we do this. So remember, we went to Phet. We did a simulation where you applied forces onto a mass, and then we looked at how the object accelerated. And for one trial, we changed the force, and the other trial, we changed the mass. So we'll walk you through that step by step. The law is very, very obvious, by the way. So here's a picture of a kid pushing an elephant. It's kind of a dangerous place to be standing for a couple of reasons, but we wanted to see how is the acceleration of an object related to the force applied to it. So we're saying how is the motion of this object affected by how hard you push on it? And it's super obvious. I think you obviously understand this if you play sports or walk around. If you push on something, it's going to affect the acceleration. So what I had to do is get data using the simulation, and I asked you to graph something. Now, in one of the classes, I actually had you graph backwards. I apologize. I wasn't paying attention on my own lab. But if you set it up the other way, it really doesn't matter. The idea is the independent variable is on the x-axis. We changed the force, then we looked at the dependent variable, the acceleration. And again, I messed that up in the lab. Um, so the idea is that as you increase the force, so let's say you apply a force, certain force gets a certain amount of acceleration. Well, if I apply more force, I get more acceleration. So what should have happened is you should have had a very, very linear function that, and it actually did go through zero. You may recall we did some best fit lining back on the bubble tube lab. So in this case, the line is extremely linear, and it does go through zero. Now, zero is not a special point, but it happens to go through zero. So I'm going to do this freehand. So you should have gotten a clearly linear relationship. And when we do that, I want to introduce some vocabulary now that we use in math class or in science class. We can say that if one variable goes up as the other variable goes up, we can say these are directly proportional. So the phrase we use for this is directly proportional. And again, that just means as one goes up, the other goes up. And it turns out as one goes up, the other goes up in exactly the same ratio. And we'll write that a couple different ways. Let me just check ahead here. So the way we often express this mathematically is if we say these two things are directly proportional, we can say that the A is, and this is where I bring in that symbol I was talking about the other day, this fish symbol means directly proportional. That's what that symbol means. So we can say the acceleration depends upon the force, and these two things are directly proportional to each other. So as I apply more force, the acceleration increases. And again, if I double the force, I double the acceleration. Triple the force, I triple the acceleration. So this is a relationship we're looking for, and this is what scientists all the time do. We look for mathematical relationships. Well, that's what you did in lab. You found that the A and the F are directly proportional. And again, that makes sense. You push an object harder, it goes faster. So that's the first big relationship I'd like you having your notes for post lab. So make sure you have your notebook out and jot down that the acceleration and the force are directly proportional, and the A and the F plot. A versus F should be a line. Again, you can stop the video whenever you need to take notes, but I will make it clear what I want you to know. Now, the second part of the lab is likewise equally as obvious, I think. It's going to ask you how is the acceleration of the object related to the mass of the object. So now we're going to apply a constant force. We're not going to change the force, but we're going to change the mass. And again, I think this is kind of obvious. Unlike the previous one, what happened is as you increase the mass of this object, as they go higher and higher masses, the acceleration should have gone down. So what typically happens, you get a plot up here somewhere where the mass is small, the acceleration is large. And as we continue getting data, it looks kind of linear, then it takes a swing. So it actually should do this. And again, you can't draw a best fit line, but you can do a best fit curve. So I'm going to do this freehand. I'm going to do something like that. And again, your labs were excellent. The data was great. You did a nice job of that. Everything worked out perfectly. Now, in this case, they're not directly proportional. As one goes up, the other does not go up. So in this case, we say they're inversely proportional. And inverse functions are something you'll take a look at more in mathematics, but you don't need to worry about the vocabulary. I just want you to understand what's going on here. As the mass went up, the acceleration went down. And you could have an indirect relationship where it's a line going this way, but if it's inverse, it actually makes this curve. So we can say that the acceleration is proportional, but it's proportional to the inverse of the mass. So as the mass goes up, the acceleration goes down. Again, we can see that from the graph. So this symbol, again, the fish symbol means proportional, and 1 over, that's an inverse. 1 over something is the inverse of something. So we say the A is inversely proportional to the mass. So that's the other relationship. And again, your data turned out perfectly. And again, it makes sense. If I'm pushing somebody who's light, I can push them, make them go fast. If I push, if Jason's on a car, for example, on a cart, and I push Jason, I can make him go a certain speed. But if Jason and Luke and Joey and 5 other people hop on the cart, the mass will go up, and therefore the acceleration of the car will go down. So again, it's very common sense. Now, what we normally do in physics, we put these two things together. So we said the acceleration is proportional to the force, but the acceleration is inversely proportional to the mass. And what physicists do and what scientists do is we put those two together. Well, if A is proportional to F and A is inversely proportional to M, it turns out A is F over M. And this is the big Newton's second law lab. So your data from Phet worked really well to create graphs, and from the graphs we can create relationships, and now we've actually created an equation. So this is how all the equations we get this year are derived. They're usually done in the laboratory like you did, although you use the simulation, it still works the same way. Now, this is called Newton's second law. And again, I've written it this way because this is how we did it in lab. We said the acceleration proportional to F and inversely proportional to M. Most people write it as F net equals ma. So in your notes, we're going to use it this way more often. It's the same equation. We're just using ESNA. We're just rewriting it. So if you ask somebody that's taken physics before, what's Newton's second law equation, they'll always go F equals ma. Now, if you look at this, we have to be a little careful about units and things like this. This is a force. This is a mass. That's an acceleration. So this is in meters per second squared. This will be in kilograms. And that's one thing about physics that's a little goofy. Masses always have to be in kilograms because a Newton, the unit for force, is defined in terms of a kilogram in a meter per second squared. Now, this is somewhat handy to think about this way. When I say, I mentioned before, the units for force are newtons. Well, what is a newton? I know what a pound is. It's, how hard the earth pulls on 7.5 bananas. But I don't know what a newton is. So what they tried to do is they tried to define a newton is it's the force required to take a kilogram. Now, a kilogram, if you lift weights, a kilogram is about 2.2 pounds. So if you hold this tiny barbell, if I want to make that barbell speed up by 1 meter per second every second, then I have to apply a force of 1 newton. So you can imagine a chunk of metal, for example, sitting here, and if I apply a 1 newton force, the speed will go 1, and then it will go 2, then it will go 3. Every second it will speed up by 1 meter per second. And again, this is a little heavy duty, but I'm trying to give you a sense of what this stuff means, because you're like me. You didn't grow up with the metric system. You grew up with pounds. So I'm trying to give you a sense of what it means. So if you took a barbell and made it go faster by 1 meter per second every second. So a newton is defined as a kilogram meter per second per second. And we're not going to write kilogram meter per second. If we have a force, we'll just write 1 newton. So N is a capital N is the symbol for a newton. And so here's your answer for force will be in newtons. So again, we typically write Newton's second law as F net equals ma, or the overall force equals ma. Now, again, just reminding you about the difference. I like how we teach it here because we emphasize that, hey, if the forces are balanced, it's the first law. Whatever the object's doing, it's going to keep on doing it. So if the object's at rest, it's going to stay at rest. If the object's moving, it's going to keep moving the exact same way. The net force, because they're balanced, 7 left and 7 right cancel, the net force is 0. The second law picks up where the first law left off. It says, well, what if the forces aren't balanced? Well, if they're unbalanced, if you don't have an equal amount on each side, then the object's going to accelerate. So we look at the net force to figure out how much that mass will accelerate. So the laws really make sense if you think of it balanced versus unbalanced, not accelerating versus accelerating. Then it works out pretty easily. Now, we have to talk about what unbalanced means. Before we said balanced meant they canceled each other. Well, obviously, unbalanced is going to mean they don't cancel each other. So a net force I like to say who wins and by how much. So that's really, and again, you can stop the video if you want, but when I say net force or the overall force, I'm really just asking who wins and by how much. So let's take a quick look at this. I'm going to close my picture here or drag it out of the way. I'm going to draw a picture here, and so here's a illustration of this process. I can't get this thing to move. Why not? Okay. Well, anyway, I'm going to draw a free body diagram of this thing. I know why not. There's this stupid video recorder screen thing's in my way. Sorry. So here's a. Oh my God! Everything's in the way. I'm closing my face. You don't miss it anyway. So it says gravity pulls a skydiver downward with a force of 600. So I'm going to draw a free body diagram. So here's the skydiver, and the force downward is going to be gravity pulls him downward. So I'm going to say that force downward is 600 newtons. So the force of gravity is 600 pulling him down. Now it says at the same time air resistance pushes the skydiver back up with a force of 460. So I want to draw, here's the force of air resistance. Now I'm going to draw this a little shorter because it's not as big. It says it's only 460. Now, to find the net force, all we're going to do is say who wins and by how much. So if I look at this picture, well, who wins? Obviously, Fg. By how much? Well, how do I do that? I just take the difference, I subtract. So I'm going to say the F net equals the winner. And by how much? So it's going to be Fg. In this case, it's Fg, the big one, minus the little one. And that's always a way of doing it. So when we say who wins, it can always be the big number minus the little number. We're looking for the difference. So the net force will be 600 minus 460, and that's going to equal 140 newtons. So the F net is going to equal 140, and that eventually will equal MA, because we have that from Newton's second law. So the key thing to starting Newton's second law problems is figure out what the net force is, and the net force is always the big one minus the little one. That's why the free body diagrams are important, so you can draw the picture from the question. Okay, so the concept of net forces is pretty simple. You're just trying to figure out who wins and by how much. Now, let's do a quick example. And again, I'm going to draw a free body diagram. I have an ice skater pushing off. So here's an ice skater. And she's going to push so that she moves forward with a force of 154. So here's the force forward. It's going to be 154 newtons. And at the same time, friction, and we'll talk more about friction later, friction is going to go backwards. But again, because it's less, it's going to be a little shorter. So I'm going to say the force of friction is 90. And again, we're asking what's the net force? Well, the net force is always the big one minus the little one, or who wins and by how much. So it's going to be the force forward. That was a bad choice of letter because they're both F. But the force forward, capital, minus the force of friction, the smaller one. So it's going to be 154, the winner, minus the loser. And that means the net force is going to equal, 64 newtons. Okay? So again, the net force is always the winning force, the bigger force, minus the littler force. Okay? We're just adding these vectors together. And you get the idea. I picked Olivia, and Molly now, and Sydney and Kira having a tug-of-war. Tug-of-war contest is a great example of this. So I'm going to have Olivia, and Molly each pull the rope east. So Olivia pulls, force Olivia 1 is 150. Force of Olivia 2 is 150. And the force of Molly is 150. So here's my object, the rope. I just draw a dot or an object. And at the same time, Sydney and Kira are going to pull with forces of 253. They are beasts. They're going to pull much stronger. So the force from Sydney is 253. And the force from Kira is 253. And the question is, are the forces, well, first of all, are they balanced or unbalanced? Is it the first law or the second law? So remember, the first law is always balanced, second law is always unbalanced. Well, if I look at this side is going to be 450. 150 350 plus 150 plus 150 is 450. So that's going to the east 450. And over here, I'm going to have 506 because I have 253 and 253. So is it the first law or second law? Well, are they balanced? Are they the same? No. So it's unbalanced. So it's the second law. And then I'm going to ask, well, if it's unbalanced, what's the net force? Well, the net's going to be the big one, 506. So it's going to be 506. Let me just clean this up a little bit. I can't. I guess I can. So F net is going to be the big force. It's going to be the forces to the right. Forces to the left minus the forces to the right. And so it's going to be 506 minus 450. And that looks like the net force will be 56 newtons. And if the force is 56 newtons to the west, which way will the object accelerate? Well, obviously to the west. So the direction is also important. The pull to the west wins. Now, I extended this a little bit. I said Olivia, and we know which one, she consumes 2 kilograms of Skittles. That's a lot of Skittles. She gripped the rope extra hard with her not quite chartreuse nails. I'm not sure I agree with Sammy, but we'll take it. And now she's able to increase her pull to 350. So now I got Olivia pulling 350, and the other Olivia pulling at 150, and then Molly's still pulling at 150. So that's going to crank this up another to 650. And so now the net force is going to be to the right because Olivia's special nails allow her to pull harder on the Skittles. So you get the idea. We're going to look at the forces pulling each direction. We're going to ask, is it the first law or second law? And if it's the first law, they should be balanced. If it's the second law, we're going to look at by how much the net force. We just take the difference. The force to the right versus the force to the left, and we add them up. So this is a basic idea. Now, the other big thing I want to talk about, and I apologize for the notes, but the other thing I want to talk about is weight. And we have to start being careful here. I've been pretty casual about talking about weight versus mass. But it turns out, and this will be super important, the weight of an object is a force. So when I stand on a bathroom scale, the earth pulls me down. So we can use Newton's second law to calculate the weight of an object. And there's the long way and the short way. So I'm going to show you the shortcut way. So this definition right here is important. The weight of an object is how hard the object pulls on you. So when I say the weight of an object, what's pulling on me is the earth. And as I've mentioned, I was much lighter years ago, as most people usually are. And over time, I've gained more mass, and therefore I've gained more weight. So the earth pulls on me harder now than it used to pull on me. We can actually calculate this by using this equation. We can calculate the force of weight, Fw, by taking the mass of the object in kilograms and multiplying by our familiar acceleration due to gravity, 9.8. Now, when we do it to calculate weight, we could call it A. When we did kinematics, we called this A, 9.8, positive or negative. Usually the convention is by physicists that when you calculate the weight of an object, we say the mass of the object times, we call the acceleration due to gravity little g. So it's just a new way of doing it. Okay, so this is a shortcut. If you ever want to calculate the weight of an object, and this is something, again, you should jot down, you're going to take the weight of the object, is always the mass of the object times this number, 9.8, which is abbreviated as a little g. And so we're going to do this in more detail later on, but so you can actually find your weight on Earth. Now, again, this is going to come out in newtons. It won't come out in kilograms. It's going to come out in newtons. So, for example, and we'll do a lab on this a little bit later. I sort of skipped the inertia balance lab, but let's take a person who has a weight of 56 kilograms, or a mass of 56 kilograms. You got to be careful. So there's my M. So if I want to calculate the weight of the person on Earth, I'm going to say, okay, the Fw equals mg. The M is 56. The G is 9.8. I'll grab my calculator. I'm doing this to show you what a reasonable number is because, again, we're using a system that we're not really used to talking about. So this is going to be 548.8 newtons. So this is actually a pretty reasonable number. A 56 kilogram person weighs about 125 pounds. You do not need to know this note down below. It's something I use it to give you an approximation, but don't worry about it. So this person, 56 kilograms, and again, a kilogram is about 2.2 pounds. So this person is about 125 pounds. And that's probably a number that's similar to many of you, not me anymore. So this is the weight. Here's the English weight, 125 pounds, but here's the metric weight. almost 550 newtons. So that's the other thing you need to know is how to calculate the weight of an object. We're going to do that quite a bit this year. Now, what I want to do, I'm going to skip ahead here, is I want to show you one example. What we can now do is we can start combining Newton's second law with our kinematics. And this picture looks horrible. This is a picture I found online. It's kids dragging a rock across a table. And I don't know why could we be dragging a rock across the table. So I called it the world's worst daycare. If you were a child sent to daycare and you had to do this, the little girl says, "Let's play drag the rock across the table." It's a horrible. Now, what we're going to do is we're going to take a look at the picture. It says a force of 40 newtons is applied to a block. So here's my object. Let me get these kids out of the way. I'm going to grab these guys and drag them out of the way. Maybe. I want to draw a free body diagram. So here's my rock sitting here. And we're going to apply a force to this rock. I'm going to drag it from rest. I'm going to pull the rock this way with a force. I'm going to call it an applied force of 40 newtons to the right. Okay. And then the friction is going to oppose it. And again, we haven't talked about friction yet, but friction always goes the other direction. So if I try dragging something, friction is going to fight me on it. So I'm going to label this F sub F. And it's going to go the other way at 25 newtons. Well, if I look at this, is this balanced or unbalanced? Well, clearly it's unbalanced. It's definitely a case of Newton's second law. One force is not the same as the other force. So I want to calculate what the net force is. So I'm going to use Newton's second law. And whenever you have Newton's second law, you're always going to write F net equals ma. That's the law we derive from lab. Now, what is the net force? Well, remember, the net force is always the big one, Fa, minus the little one, Ff, and that equals ma. Okay. And we have all these values except for a. We have the Fa, we have Ff, and we have m, so we can find a. In kinematics, if you look over here, it says the block starts from rest. Well, over here, that sounds like Vi equals 0. And it says calculate the final velocity of the block. Well, I want to know Vf. And they told me the time that the block was dragged was 5.5 seconds. Now remember, in order to use kinematics, we have to have A. A is the only variable in all the kinematic equations. Well, the nice thing is now I can find A. A is going to equal Fa minus Ff all over m. I just divided both sides by m. Well, now I have the numbers. So Fa is 40, Ff is 25, and m was given up here in 4. So if I grab that, I'm going to have 40 minus 25 equals 15. Divide that by 4, and I got 3.75. So my acceleration is 3.75 meters per second squared. Well, now I can bring that over here, 3.75. And now we can combine. Before I had to give you the A, or we had to have it in free fall, but now we can actually figure out A using the law you derived in class, Newton's second law, saying, hey, the acceleration depends upon the forces and the mass, and now I can get that acceleration. So now there's my snooze. So now I can get Vf equals Vi plus At, our kinematic equation number 1. Again, Vi is 0, so let's get rid of it. So I can say, how fast is that block moving now? Well, the block will be starting from rest, speeding up at 3.75, and we'll do that for 5.5 seconds. And so now I can go 3.75 times 5.5, and I get 20.63. So the final velocity is 20.63 meters per second. So again, this is kind of how they find velocities of cars or athletes. Sometimes they'll have a football player and they'll say this guy started in the backfield at rest and he ran at a certain speed. They can figure out the speed and they can figure out the force and figure out the acceleration. So, a lot of, I keep on mentioning sports because sports are something where people use physics to optimize performance. So if you're playing football or baseball or basketball or whatever it happens to be, this is a place where, or you're dragging a rock across the table, this is a place where you can use physics to help you figure things out with cars and whatever. So again, we're going to combine Newton's second law, F net equals ma, with our kinematics that we learned before. Now, there's a whole bunch of other problems. I'm not going to do them all. Pitchers make a lot of money throwing a ball, especially if you're left-handed. I guarantee they pay attention to the mechanics and the physics of throwing a ball. These guys get paid millions of dollars. So there's a million examples. Ice skaters, this is Michelle Kwan, I think. They all use the physics behind this. So you're going to get a homework from the sub if I'm not here, and it's going to basically walk you through. It's going to have you on the front. It's going to have you draw free body diagrams. Make sure your units are the proper. Make sure your velocities are meters per second, accelerations meters per second squared, distance in meters, times in seconds. The mass, pay attention. The units give away. If it says kilograms, you know it's a mass. If it says newtons, you know it's a weight or a force. So you go ahead and try that homework. Um, and again, I'll be back, and hopefully I'm not out of school anyway, but we'll get back and we'll figure things out. I just want you doing something, having some notes and starting the homework if I'm not in class today. All right. We'll stop there, and hopefully that worked out well.